Imagine how the ancient engineers keep homes cool in plus 120 degrees Fahrenheit heat without shade. The desert sun scorched every surface relentlessly. Temperatures rose above anything a modern city usually experiences. Despite this, communities remained surprisingly comfortable inside their dwellings. Ingenious design, careful material choice, and observation of natural forces made cooling possible. Their survival depended on understanding airflow, shade, and thermal properties deeply. Life in extreme heat required constant adaptation and careful planning. People woke early to avoid midday intensity. Shadows became precious indicators of safety. They studied wind movement and air currents across open plains. Even small breezes were harnessed to cool interiors efficiently. Children learned these patterns naturally through play and observation. Every movement and activity respected the rhythm of the sun. Walls shaped airflow and controlled temperature expertly. Narrow openings allowed cool air to enter homes steadily. Higher vents enabled hot air to escape naturally. Thick stone and clay walls absorbed heat slowly. Insulated interiors maintained stability despite relentless solar radiation outside. Families positioned sleeping and working areas strategically to stay comfortable. Children instinctively moved to cooler spots throughout the day. Roofs played a critical role in passive cooling strategies. Slanted surfaces redirected sunlight away from living spaces. Thick thatch layers blocked solar penetration efficiently. Light-colored materials reflected intense heat naturally. Roof chambers trapped hot air, directing it upward safely. Over time, villagers perfected these designs through trial and observation. Children watched elders adjust vents and roof openings carefully. Earth-based structures contributed remarkable temperature moderation. Partially underground rooms remained cooler than scorching surface levels. Thick earthen floors and walls absorbed heat slowly. Interiors stayed comfortable during the peak afternoon hours. Builders sometimes layered floors with damp sand or clay to increase cooling efficiency. Children learned to sit or play on these surfaces, instinctively, feeling relief from the sun. Water was leveraged cleverly for temperature control. Clay vessels stored water strategically inside homes. Evaporation released coolness gradually into living spaces. Builders positioned jaws near breezeways for maximum effect. In some cases, underground channels circulated water subtly beneath floors. This technique provided cooling without direct exposure to sunlight. Children observed and learned the effects through daily routines. Wind towers captured breezes from higher altitudes efficiently. Air funneled downward through internal shafts, cooled along shaded surfaces. Rising hot air escaped easily through upper openings. Wind towers worked consistently without mechanical assistance or shade. Placement required precise understanding of prevailing winds. Children became familiar with these currents, playing in courtyards and corridors. Color selection amplified natural cooling effects. Light clay, pale plaster, and stone surfaces reflected sunlight effectively. Interiors remained cooler because walls absorbed less heat overall. Communities understood color as part of engineering design intuitively. Children observed color differences and learned which surfaces remained comfortable during intense afternoons. High ceilings allowed hot air to rise above living areas. Heat naturally moved upward toward rafters and vent openings. Cool air replaced rising warmth at floor level. Children slept or played in lower areas, benefiting from vertical airflow. Builders refined ceiling height through observation, enhancing comfort without modern tools. Courtyards and open spaces enhanced temperature regulation. Nighttime air cooled stone and soil gradually. Morning warmth released slowly from surfaces, stabilizing interior temperatures. Breezes passing through courtyards entered homes efficiently. Courtyards functioned as both social and thermal spaces. Children learned how to use shaded corners and breezy zones effectively. Nighttime cooling reinforced daytime comfort. Builders opened upper vents before sunset. Cool night air filled walls and floors, storing energy. Thick walls retained coolness for the following day. Families rested during the hottest hours, while interiors stayed comfortable. Children experienced predictable patterns of cool airflow every night. Material layering improved thermal efficiency further. Dense stone slowed heat absorption. Porous clay released moisture gradually to reduce air temperature. Straw, reeds, and thatch layered strategically for insulation. Builders combined materials intuitively for maximum comfort. Children helped carry small bundles and learned tactile differences in materials. Narrow, recessed doorways minimized direct sunlight entry. Doorways angled to block harsh rays efficiently. Light entered softly, while interiors remained shielded. Thresholds acted as airlocks, reducing unwanted heat flow. Children naturally gravitated to shaded areas created by door recesses. Placement decisions evolved through repeated observation over generations. Vegetation enhanced cooling subtly, but effectively. Hardy shrubs, planted near doors, shaded ground surfaces. Even minimal shade altered heat reflection locally. Plants also cooled wind, entering homes through evapotranspiration. Builders integrated natural elements into architectural designs. Deliberately, children learned to move near plants to gain relief. Thermal mass created by stone, earth, and floors regulated temperature consistently. Walls absorbed heat during daytime slowly. Floors stored coolness from night air efficiently. Interiors maintained stable temperatures without requiring shade or machinery. Children instinctively used cool zones near walls and floors. Communities thrived, despite blistering midday sun. Underground storage rooms provided dual benefits. Food and water remained cool naturally. Rising air from storage rooms cooled upper floors. Builders optimized airflow between subterranean chambers and living areas. Children helped transport goods while benefiting from comfortable temperatures. These strategies integrated survival needs with thermal engineering. Behavioral adaptations complemented architectural strategies perfectly. Families scheduled work during cooler hours. Children played in shaded, breezy corridors. Routines aligned with natural cooling cycles, reducing exposure. Movement was deliberate to minimize heat stress. Knowledge became instinctive through daily practice and observation. Wind corridors between clustered buildings enhanced cooling naturally. Narrow alleys accelerated airflow through adjacent homes. Breezes gained strength while moving between walls. Communities arranged houses intentionally to exploit wind channels. Children experienced accelerated airflow during walks or games in these alleys. Villages relied on natural dynamics instead of artificial devices. Moisture-based cooling improved comfort subtly. Dampened cloth hung in doorways released evaporative cooling gradually. Porous clay surfaces emitted micromoisture, cooling nearby air. Even minimal moisture, combined with airflow, enhanced interior comfort. Children observed and learned handling methods while moving through homes. Material durability ensured long-term cooling. Clay and stone strengthened over repeated heating. Surfaces absorbed and released heat efficiently for decades. Builders studied material behavior carefully over generations. This knowledge informed the placement and combination of walls, floors, and roofs. Children participated in maintenance tasks, internalizing the engineering principles naturally. Daily observation refined construction techniques continuously. Builders noted airflow patterns, sunlight angles, and wall performance. Subtle adjustments improved cooling efficiency with every generation. Children learned these lessons through participation rather than formal teaching. Communities survived extreme heat without shade, fire, or machines. Cultural practices reinforced cooling strategies consistently. Songs, storytelling, and daily routines embedded environmental knowledge. Children absorbed practical principles without needing explicit instruction. This knowledge preserved architectural intelligence across generations. Cooling systems became as much social as functional. Even small architectural details enhanced thermal efficiency. Stone benches absorbed coolness from night air. Elevated platforms minimized contact with heated floors. Strategic openings directed airflow into interior rooms. Every minor adjustment reinforced passive cooling. Children understood these small effects through daily experience. Fire sometimes aided indirectly. Burned clay improved insulation in walls. Kilns hardened bricks for greater heat resistance. Communities utilized heat-hardened materials for long-lasting comfort. Children assisted with preparation, observing transformations that contributed to survival. Homes were living systems finely tuned to extreme climates. Architects balanced airflow, shading, thermal mass, and water strategically. Communities adjusted layouts continuously based on seasonal changes. Children participated naturally in daily activities, reinforcing passive cooling knowledge. These integrated systems ensured survival in plus 120 degrees Fahrenheit conditions. Patterns of airflow, material science, and solar reflection combined seamlessly. Wind, earth, water, and human behavior were all part of design. Builders created dynamic interiors that felt cool despite intense sun. Children navigated homes instinctively, benefiting from centuries of experimentation. Cooling was practical, sustainable, and ingenious without modern technology. Ancient engineers proved survival under harsh heat is possible. Their innovations reflected deep observation, trial, and environmental mastery. Homes remained safe, comfortable, and functional even during extreme temperatures. Children absorbed knowledge through observation, play, and participation daily. Communities thrived through architecture intelligently shaped by climate. Lessons from these engineers remain relevant today. Passive cooling reduces energy usage dramatically. Modern architects still borrow techniques like airflow channels, thermal mass, and reflective surfaces. Ancient practices offer inspiration for sustainable living in extreme heat. Children learn principles that guided survival and comfort instinctively. Even without shade or electricity, these homes stayed remarkably cool. Air flowed naturally. Materials absorbed or released heat effectively. Water, wind, and walls acted in concert daily. Communities thrived through intelligence, observation, and ingenious engineering. Ancient homes remain a testament to human adaptability, resilience, and creativity under extreme heat. If this changed how you see ancient engineering, hit that like button and also subscribe this channel for more rediscovered genius. And tell me in the comments, what other mysteries should we uncover next?